Continuing along with what we've been talking about. Here we go. All right. So let's just get it titled and then we'll talk about it in a second. So this is lesson 9. Arithmetic sequences and linear equations. Arithmetic sequences and linear equations. Now, today we're going to do a little bridging the Algebra 1, Algebra 2 gap, and hopefully you'll see, again, how these things are all connected. Now, I'm going to be very specific with you about the placement of certain things on your notes. You're going to have to follow what I'm telling you, or you're going to not have the space to write the things, because I'm going to put stuff in different places on my paper, and I'll tell you where to put those. So try to make your notes look like my notes to be as successful as possible, okay? So you should have your title up top there, and we'll just call this example 1. And we'll start off by saying, consider the sequence. All right, now, here's the first adjustment. I want you to write, consider the sequence here on this line on your paper, and then I want you to count down 6 lines, 6 spaces. So 1, 2, 3, 4, 5, 6. And then kind of about here-ish, maybe depending on your writing, I want you to write this, 8, 11, 14, 17, dot. Okay, so let's consider this sequence here. What do we know about the sequence? Okay, so that makes it what kind of a sequence? Arithmetic, right? Arithmetic. Okay. And when you say it goes up by 3, can you be more specific? Okay. Go ahead. Okay. Okay, so the common difference is 3, right? So let's just make a couple of, like we do here. Our common difference is 3, right? Now, the other thing that you almost assumed, just because I wrote this up here like that, was you almost assumed that this is the first term in the sequence, making this the second term in the sequence, and the third term in the sequence, and the fourth term in the sequence, right? But you did. That's what you guys did. You looked at that and you said, hey, look at that. That starts and then goes up by 3. Well, and that actually is going to be a question that we're going to have to look at is, are there terms before it? Are there terms after it? Are there terms in between? Can you have a 1.5 term? Oh, let's see. Let's talk about it. All right. Now, I'm going to give you a different perspective on looking at our sequence. Right. So we just wrote a sequence here. Okay. Let's do a different perspective. Take your straight edge. Come out here to your red line. Okay. Draw yourself a line out here like this. So you used your straight edge right now. Use your straight edge and you drew yourself a line like that. All right, now you can either use your straight edge or you can just sort of wing it here. And actually, let's make a note so that we're clear. On the top here, we were notating our Okay, I don't want to start using names, so let's lock it in. Okay, so on the top, we were notating term number, and on the bottom, we were notating our sequence value, right? So it was the value of the sequence and the term number. Okay, so we're going to leave it like this for now. Okay, and then here's what I want you to do is I want you to leave just a little bit of space in here, like, I don't know, maybe about that much space, right? And then from where you drew your straight line right here, I want you to count down 1, 2 lines here, and then I want you to draw another straight line across like that. So you're going to count down 1, 2 lines. You're going to draw a straight line across like that. And then you're going to do another one like this. I got a little crooked. Okay, now, here's what I'd like you to do. We're going to put a hash mark here, and a hash mark here, and here, 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 here. All right, we're going to number these like this. 3, 6, 9, 12, 15, 18, and such. Now, going across here, this direction, you want about the same amount of distance this way as you have this way. And so we're going to go hash mark like this, and then hash mark, and then hash mark, hash mark, hash mark like that. And we're going to number these 1, 2, 3, 4, 5, and such.
Oh wait, I put 6 hash marks.
That's okay. Now, I'm going to connect these together. So the numbers down the bottom here, the 1, 2, 3, 4, 5, we're going to call that the term number. And then over here, we're going to have the sequence value.
Wait, but why are there only 5 if there's 6 sequence values?
Well, there's really only 4 term numbers.
Oh, you just added extra?
I just happened to put an extra one on there. Maybe we'll see if we can figure it out if there's another one. Okay, now I want to point something out, right? Let's go back and talk about our sequence that we wrote out here, right? You told me that it had a common difference of 3, right? What you looked at was the change going up here in the sequence value, right? But there was also a change that occurred with the term number. What happened there? Like, can I say this? Like, every time my sequence value went up by 3, what was that? The term number increased by 1, right? So there's sort of a kind of a dual thing happening here, right? This is increasing by 1. So every time this increases by 3, this is also increasing by 1. Increased by 3, this is increasing by 1. Yeah? Thought? Okay, let's do this. Here's what I'd like you to do. You listening carefully?
Yes.
Okay, what I want you to do over here in this little kind of graphy looking thing that we made, I want you to draw me the discrete picture for this sequence.
If that is the first term.
Well, now we've defined it as the first term. We're not assuming any longer. Now we've defined it. Okay. Draw me the discrete picture of this graph. Ready, go. Drew the correct discrete picture. It should look like this. Should there be anything connecting those points? Okay. Should there be anything connecting those points? Wait, that's not the answer to the question. I asked is, should there be?
Yes.
No, there shouldn't be. Why shouldn't there be? Because I said it was discrete.
Oh my god.
Could there be? What would I connect those with? A line? Well, I don't know. Okay, well, what were our connecting straight paths? We had lines, rays, and segments, right? Okay, well, we could do a segment for sure, right? Because we for sure have this like through to here. But let me ask you this: does the sequence continue up? Okay, all right. So we could actually put a 5 point, huh? Okay. Could we put a 6 term or a 7th term? Okay, all right. So then we should be able to take this and put an arrow on it.
So it's an array. It's a ray, right?
Currently, it's a ray.
Did we put that on it?
Okay, hang on. Hold on a second. Now, here's where we're going to get a little weird. Okay. Can I extend my sequence this way?
Yes.
I can?
No, there's no dots at the first term. We established that.
Well, okay, but I mean, if I just took a term and I added 3 to it, I could take away 3. Well, okay, let's just think about this for a second. Okay, let's just say what if we were to have another space this way? Yeah, right? So you guys have heard me mention this, right? So this would be like the 0th term, which would be what? 5, right? It would have to be 5 because if we were at the 0th term to get to the first term, we would have to add 3, and this would have to go up by 1, right?
Yeah.
So to be consistent, I'll write it as a plus problem, because really our common difference is a plus problem we write, right? When it's getting smaller, we write it plus a negative value, right? Okay. Now, over here, there's usually like some letters that are associated with like a left and right tracking and an up and down tracking. And oh, okay. All right. Sure. We're doing an X and a Y style graph. So then our term numbers really are our X values and our sequence values are our Y numbers. Now, wait a second. You guys just said I could have a 0th term, right? So that means I can extend my line this way, right? And oh, look at that. It crosses the graph at like kind of 5-ish, huh? Can I have a -1 term? So how would I get a -1 term? What would -1 term be? Well, it'd be -1 comma something, right? 2, right? So, okay, so here's where it gets a little strange, right? We can continue our graph this way. And not only can we have the first term and the second term and the third term, we can have the 0th term. And if we make it continuous, we could have a 1.5-ish term or a 2.75-ish term. Because if we're increasing this in these kind of continuous fashions, we could just break down that common difference and, make it fractional by nature. Okay, all right. So let's do this. So we said that the common difference, like from the first to the second term, right, was an increase of 3. So like this here was plus 3.
Rise over run. Jane literally said that.
This here is plus 1. Okay, all right. Okay, so rise over run. There's a fancy math way of writing that, and if you want to just sort of kind of call it in, it was the change in the y values over the change in the x values. Okay, question. I got a question for you. What if I started at the second term and I jumped right to the 4th term, like second to 4th? How much change in the sequence value is there? Plus 6. Okay, so if I went from the second term to the 4th term here, what would be the change in values? So this would be an increase of 2. term numbers. So let's look at it here. So here to here, this is plus 2, and this is plus 6. Anybody tell me? Oh yeah. Wait, here. Let me put that right there. Let me put this right here. Okay, wait. Now, this is the change in y, and this is the change in x for the orange one. Okay. It's plus 2 and plus 6. Okay, question. Are those triangles congruent?
No.
Well, why aren't they congruent? They're similar? What does that mean? Yeah, no, you got this. Go, Lauren. That is excellent. You pulled that back. Okay, and but how do we know they're similar triangles? What can we say for sure? No. Okay, they have a common angle. But unfortunately, we needed 2 angles, and we don't know either of the other 2. Okay, so we have no, they're not. We don't know they're supplementary. Not we don't have that. No, linear pairs. Nice try, Tyler. You're just throwing out geometry terms. Okay, so listen. We had 3 ways of proving similar triangles. Number 1 was angle, angle. Number 2 was side, side, side. And then there was side, angle, side. But hang on. Okay, now, hold on. Let's bring this full circle. In order to use side, angle, side similarity, we had to have the common angle in between the 2 sides, and the ratio of the 2 sides had to be proportional. Okay, now, is that true? Is the change in y, 3 over 1, the same as the change in y, 6 over 2? Okay, and we know that because we can cross multiply, and we end up getting 6 equals 6, and so we do in fact to have similar triangles. Okay, remember all this? Starting to come back a little bit?
Wait, but they're similar because of which one? Is it angle side?
Side, angle, side. Because the angle is sandwiched in between the 2 sides. All right, now one more thing I want to do. I guess I should have told you guys to get out your highlighters too. If you got a highlighter handy, grab out your highlighter. Okay. All right, here's what I want to do. Let's box this whole thing here. And then let's box this whole thing here. And then right here, we're going to say... And right here, we're going to say... Because what we want to get used to, KK, is we want to get used to understanding that there are 2 ways to look at a coin. From the head side of the coin and the tail side of the coin. Okay? There is the algebraic side. In this case, it's our sequence, which we morphed into a table of values, which we then turned into a picture. And not only did we turn it into a picture, hang on. Not only did we turn it into a picture, we used our understanding of geometry to prove that those changes right here that we see 3 and 1 and 6 and 2 are the same using similar triangles. All right, let's kind of summarize this up a little bit. Here we go. So we're going to kind of summarize this up by saying the change in the sequence value divided by the change in the term number on the head side of the coin is the same thing as, Geo, is the same thing as, on the graph side, the change on the y-axis in comparison to the change on the x-axis. Or we could say this. And I'm going to put this in parentheses, simplified D. What's D? Okay, so we'll put it in quotes. Common difference is the same thing as the simplified common difference is the same thing as the ratio of the change in y's to the change in x's. That had a fancy math word when we were graphing lines in Algebra 1.
Algebra 1
begins with an S. Slope. Yes. The slope. We'll put in parentheses here of a line. Okay, I told you we were bridging the gap today. Okay, we were bridging the gap today. So now we're making the connection between arithmetic sequences and graphs of lines. Specifically, now we know the common difference is the same thing as the slope. That's going to become important for us. Okay, give yourself a squiggle. Okay. We're going to make 2 sections of our paper here. I don't want you to divide it because I want you to keep it open, but just think in terms of we're going to work on this side first and then we're going to work on that side, okay? So, here we go. Let's write the explicit formula for the example above. Okay? Let's write the explicit formula for the example above. I'll get us started. The generic explicit formula is some term in the sequence is equal to the first term plus the common difference times the term number minus 1. Everybody remember this, okay? Yes. All right, this is the generic explicit formula. Okay, so if we wanted to start writing out our explicit formula, we're going to start with the unsimplified explicit formula. So go ahead and write down what is the unsimplified explicit formula for the sequence that we were just working with above. Go ahead, you do it. To put? Yeah. Good? All right. Now let's simplify the unsimplified explicit formula. So first thing we got to do is some little distribution, right? All right, so then we get a sub n is equal to 8 plus 3n minus what? 3, right? Don't forget to distribute both terms. Combine our like terms, and as I showed you, I want you to write your explicit formula with your n term first. So it's a sub n is equal to 3n plus 5. Okay. All right. Now, question. What is that? That's the common difference, right? That's the D. That's the common difference. We're working on explicit formulas. Wait, we're using Algebra 2 language. We're talking about sequences. So you have to use all the right language. That's part of the trick of this lesson. Can you use the right language or recognize the correct language I'm talking about and produce the right answer using the right language? Of course, this is the simplified. We'll just put that again in parentheses. The simplified D. What, hey, what's this? No, B is not Algebra 2 language. Good try. Thanks for playing. Okay, how would I write that with a little shortcut? The 0th term. How do I write the first term? A sub 0, exactly right. This is A sub 0. That's the 0th term. Of course it makes sense. I'm teaching it. Why wouldn't it make sense? You guys know what you signed up for. Excellence at its best. Okay, all right, here we go. So this then, this is our explicit formula. See? Everybody good? We wrote these for the last quiz, so you should be good. All right, now, let's do a little throwback, like I said. Equation of a line. Okay. All right. So the equation of a line, let's start with the generic equation of a line, which is y equals mx plus b. This is the generic equation of a line. Just like that's the generic explicit formula of an arithmetic sequence. And they don't look the same, do they? Okay, but
when you simplify it.
Well, let's see what happens. Now, there are, just like there are a couple things we need to replace in our generic, we need to do some replacing of some things here. Now, we kind of already figured out what the m is. M is slope, right? But let's just jot it down to put a little math to it. So if in Algebra 1 we were calculating the m, we would do something like this. Yeah, you remember this? Right? y2 minus y1 over x2. I know, I'm giving you guys PTSD now, huh? Okay, now, it doesn't matter. I'm going to let you look at your paper. It doesn't matter which, we need 2 points, right? We got to pick 2 points, right? And it doesn't matter which ones we pick, but this has to be a partner pair, this has to be a partner pair, and these have to be subtraction problems, right? So, like, I could use the ordered pair from my graph above. I'm going to use 3, 14. And I'm going to use, the other one I'm going to use is, I'll use 1, 8. Okay, so 3, 14 and 1, 8. So if I use 3, 14 and 1, 8, I'm going to go 14 and 3.
What?
And it's a subtraction problem. And then I'm going to go 8 and 1. And again, this is a fraction. And 14 minus 8 is 6. And 3 minus 1 is 2. And simplify is 3 over 1. Or when we write it as m, we wouldn't write it 3 over 1. But what we know is if we read this, it's up 3, right 1, up 3, right 1, up 3, right 1. Or it could go down 3, left 1. Oh my gosh, Quinn. Say it again a little bit louder, Quinn. Which does what? Does what? It goes along with our sequence. Very good. Look at you guys learning math. Didn't think it was possible, did you? Okay. All right, now let's talk about. Okay, that was one thing that we had to do. We had to come up with. We had to come up with this, right? Because remember, right? Our x's and our y's can be anything, right? When we write our linear equation, we're gonna have a y and an x in there, but we got to have a number here and we got to have a number here. Okay, so we figured out how to find this one. We do the slope formula. Does anybody remember how to find this one in Algebra 1? It is the y-intercept. Good. Okay. But how did we find it algebraically? Okay. But how did we find it algebraically? All right. Let me give you a couple tips or reminders here. You ready? Here we go. So the first thing we did was we would leave an open spot for y, and then now we know our m is 3, and we would leave an open spot for x, and then we would have plus b. Now, if we have a line that connects all of the x's and y's, all we have to do is pick any point on the line and use the x and the y coordinates for those points, right? So, like, I used what I used, 3, 14, 1, 8. Let's use 2, 11. So 2, 11, that means I'm going to put the 2 here. I'm going to put the 11 here. And then I'm going to solve for b.
Easy
11 equals 3 times 2 is 6 plus b minus 6 from both sides. And what do you get? 5 equals b. You can do this with any of them. Let's just do 14 and 3 real quick. Put a 14 here, put a 3 here. No, let's just do it quick. So 14 and 3, right? So 14 minus 9. 5. It's always going to be 5. Because it's the same line connecting it together. Now, lastly, once you have these two numbers, you wrote your linear equation. Y equals, now you went back to your generic y and x's. Y equals 3x plus 5. It's literally the same thing. Wait, no, it gets better. No, wait, it gets better. Okay, what is this? No, what is it? No, we're not using Algebra 2 language. Now we're using Algebra 1 language. Okay, this is slow. You see what I'm doing? I'm bridging the gap between Algebra 2 and Algebra 1. Okay. Miss Robinson. Miss Robinson. Haven't heard that name in a while. Okay. All right, and what is this? This is the y-intercept, which is where our graph crosses on the y-axis. Okay, this is a blood pressure check, or a heart monitor check, or an oxygen level check, or a check your weight, check your height. This is one of those, biometric readings we talked about a while ago of how we assess things. This is another one. This is another one. This is another one. In different languages. In Algebra 1 language, here, and in Algebra 2 language, there. Okay, so, if the lesson title is, ready? If the lesson title is Arithmetic Sequences and Linear Equations, now you can see that we have the same thing. Okay? Do I give this to you now? No, we'll wait. No, we'll wait. No, I got one more to tie it together, but I'm gonna wait. No. You don't want to wait for this. You want the good stuff. It's like the he was Kaiser Soze? What? No. Okay. All right. If you don't know what I'm talking about, go back and watch the video and figure out what I'm talking about. Okay, ready? Here we go. What? Yeah. Unless I'm not done, and then we stay. Okay, ready? Here we go. I want you to skip down. So you write your title at the top. I want you to skip down 1, 2, 3 lines. And then kind of out here, you're going to go ... and then -7. And then ... and then -3. And then ... and then 5, and then ... 11, and then ... Okay, so now it's really kind of much harder because now it's very clear that I can't just assume that -7 is the first term. And I'm going to tell you, I'm going to go the other way, watch. I'm going to tell you this is, in fact, the 7th term in the sequence. And this is the 4th term in the sequence.
Wait, so there's like multiple in between.
And this is the term in the sequence. And this is actually the -2nd term in the sequence. Okay, so here are my questions. Number 1, is this arithmetic? And how can you prove it? And if it is arithmetic, then what is the explicit formula slash linear equation, since we know that those are the same thing now. Okay, so we have this sequence excerpt. We know the negative second term, the fourth term, the seventh term. We want to know, is it arithmetic, and how can we prove it? And if so, what is the explicit formula and or linear equation, since they're the same thing? All right, let's do a little squiggly squiggly. All right, let's drop down 1, 2, 3, 4 spaces, and then right here I want you to put an X, I want you to put a Y, and then with your straight edge I want you to make yourself a table that runs out like about yay-ish. Okay. All right, some things I know, right? From my previous example, I was tracking term numbers as the X and sequence values as the Y, which means that the negative second term's value is negative 7. And the, well, I don't know that one, the term is negative 3, and the fourth term in the sequence is positive 5, and the seventh term in the sequence is positive 11. Okay. Well, okay, here's something that we kind of proved on the front side of our paper, and that is that the change in Y and the change in X was what we used to describe the common difference. The simplified change in Y over change in X, right? So let's just pick one. Like, let's say, what if we went from this sequence value to this sequence value? What is the change in the value of the sequences? Okay, so this is it increase or decrease? So this is increase of 6. And what do we got up here? Increase of 3.
Is that a ratio or what?
Looks pretty ratio-ish, huh? Especially if we come over here and say, well, this was an increase of 6 and an increase of 3, which simplifies to what? No, not 1/2. 2 over 1. We need to go back to prime factoring and simply fractions. All right. Okay, but that was just one. Like that could be a lucky guess. What if we did, let's say I started at the 7th term and I went all the way down here to the negative second term. Okay, here you go. I'm out here at positive 11 and I want to go all the way down here to negative 7. Well, okay, if I'm out here at positive 11, how many steps do I have to take to get to 0? 11, right? And then I got to go to negative 7?
18.
Up or down? Okay, so that it's negative 18. Okay, well then what would it be from here to here? 7 to negative 2. Okay, negative 9, right? So then my green change in Y over change in X is negative 18 over negative 9. What does that simplify to? Oh, that simplifies to 2 over 1. Wait, so now I don't have to have consecutive terms to find the common difference. I just need to compare the change in the sequence value to the change in the term number. That seems kind of powerful. That's almost like going from an Allen wrench to a power drill. Okay, so question, is this sequence that I gave you, this excerpt up here, part of an arithmetic sequence? How do you know that? Consistently, right? Okay, so This right here, these two answers, this one and this one, for us, here I'll do a little swoopy arrow. This confirms, watch this one. Remember this language? A constant, I can write that better. Okay. A constant, watch this, constant rate of change. Confirms a constant rate of change. That's another language. In other words, slope. Or common difference, depending on are we using Algebra 1 language or Algebra 2 language. Okay? So we have proved this is arithmetic. How did we prove it was arithmetic? Because we showed that there's a constant rate of change by evaluating at least two pairings of numbers and determining that the change in sequence value compared to the change in term number is constant or consistent in two different situations. And we could continue to do it, but 2 is good enough for me. Okay? That's how you prove it. So if I ask you to prove it, you have to show me two comparisons of change in sequence value to change in term number, and they have to be the same in order for you to be able to say that that is, in fact, a common difference. So no, we're not there yet. So yes, this is arithmetic. Yay, we did it. Okay. All right, now, here we go. I'm going to give you the simplified explicit formula. So kind of what we just sort of came up with up above. Simplified explicit formula. What language am I using? Algebra 2 language or Algebra 1 language? Algebra 2, good. Okay. And that looks like this. A sub n is equal to dn plus a sub 0. Do you understand what that means? A sub n is equal to d times n plus a sub 0. Could you tell me what each one of those terms means in there? Okay, right? A sub n is any term in the sequence. D is the common difference. N is the term number. A sub 0 is the 0th term. Okay, good. All right, now, we now know from the example that we were just working with right now that D is equal to 2. We figured that out from above. So we've got the D part, right? And again, just like we did with our y equals mx plus b, we needed the m and the b. What we need is the d and the a sub 0. If we have the d and the a sub 0, we can write any explicit formula. So the common difference and the 0th term are really the keys to writing an explicit formula quick and easy without having to do any of that simplification work. Does that make sense? So if you find the d, you get it by comparing your ratios of rate of change between your sequence value and your term number. And now we got to figure out how we're going to come up with the 0th term. I'm going to show you kind of a different way of looking at it. So we're going to say that a sub 0 can be found by this right here. The change in y over the change in x for the example above is 2 over 1. Okay. Yep, let's finish it up, all right? So, where we left off in class, what I was saying was once we now know our simplified explicit formula, then really all we need to be able to do is find our common difference, which of course comes from comparing our changes in sequence value in comparison to our changes in term number. That's how we get our common difference. And then if we can find the 0th term, we can plug those right in to find a very quick simplified explicit formula. Then we don't even need to go through this whole process that we did right here where we start here and then work our way down. So let's see if we can calculate that. Now up above here, right, we came up with our D equals 2. So we already know what number's going in here. So now we just got to figure out our a sub 0. And again, I started to explain this. So a sub 0, right, we can find it this way. So let's create another proportion here, right? Proportions are two ratios that are equal. So this is, I'm saying the same thing as I just said right up there, right? Is the change in y over change of x is equal to 2 over 1. That's the same thing I just said up there, okay? Now, let's do this. Let's pick from our table of values here some term number to start with. like I'm just going to pick randomly. I'm going to pick the 7th term. Okay, now think about it this way. If I was at the 7th term number and I wanted to get to the 0th term number, how many steps would I have to take to get from 7 to 0? Well, I would have to take 7 steps down, right? It would be like down 7 steps that way. So what I'm going to do is I'm going to replace my change in x like this. So I'm going to go my change in y over down 7, that's my change in x, is equal to 2 over 1, right? Because now what I've done is I've created a proportion that I can solve using cross multiplication, right? I'm going to rewrite this so it's the other way around. So I'm going to do my change in y times 1. Well, that's just going to be the change in y. And then I'm going to do 2 times negative 7. So that's negative 14. So what I'm saying here, when I come up with this change of y value is negative 14, that means that if I went from here down to the 0th term by taking 7 steps down that way, then I'd need to start here and take 14 steps down to get to the sequence value of the 0th term. And so in this case, I can say that my a sub 0 is equal to 11 take away 14, right? My sequence value of 11, I need to take 14 steps down to get to my a sub 0. And 11 take away 14 is negative 3. Oh, wait a second. From 11 to down here, 14 is negative 3. Wait, what term number is this? Yeah, that's the 0th term, isn't it? Okay, we figured that out now, right? Because we got confirmation that our a sub 0 is at a sequence value of negative 3, right? Okay, and I mean, we can do this with any of them, right? Watch, like, let's just say that, again, I'll just do it with a different set of numbers. So my change in y over my change in x is equal to 2 over 1. Once I know my d, I can just set this up, right? And then I could say, okay, what if I started at, let's just do this one. Let's say I started at the negative 2 term and I wanted to get to the 0th term. Well, I would have to go up 2, right? Because I'm starting at negative 2. I got to go up my sequence value 2 points, right? So if I replace this, I'm going to go change in y over positive 2 is equal to 2 over 1. Again, I'm going to cross multiply and solve like that, right? And so I'm going to get my change in y is equal to positive 4. Now you say, well, okay, hang on a second, Mr. Farkas. I thought the change in y was negative 14. Well, it is if you're starting at the 7th term number. But when you're starting at the negative 2nd term number, the change in y to the a sub 0 is up 4, right? So then, again, I can see, you can already see it happening here, can't you? Look, from negative 7, if I go up 4, I'm going to get to negative 3, right? So my a sub 0 is going to be negative 7 plus 4, because this is a positive 4, right? Negative 7 plus 4. And that's going to get me negative 3. So it doesn't matter which term value I start with. So to figure out your a sub 0, you just pick a starting term and how many steps do you have to take to get back to 0, right? And then once you have that, then you can solve your proportion and come up with your a sub 0 number. All right, now, here we go. This was the thing that I wasn't going to give you earlier in class, and I'm just going to make you wait for it now. Ready? Here we go. Okay, so let's kind of summarize this whole thing up, right? I've been talking about the difference between Algebra 2 language and Algebra 1 language, right? So for this particular problem up here, now that we have our d of 2 and our a sub 0 of negative 3, then I can easily jump to writing my explicit formula is going to look like this, right? My explicit formula, that's Algebra 2 language. We're dealing with arithmetic sequences. So it's going to be a sub n is equal to 2n minus 3, right? This is my Algebra 2 language, my explicit formula, like that. But I can also write this as an equation of the line, right? An equation of the line. If I write it as an equation of the line, well, then I'm using my y equals mx plus b. So then this is going to be y equals, now I know my common difference and my slope are the same thing, so this is going to be 2x, and I know my 0th term and my y-intercept are also the same thing. This is going to be minus 3. And if you were like, wait a minute, how did you know that the 0th term and the y-intercept are the same thing? Go all the way back to the graph at the beginning of the lesson. Here is the 0th term. The 0th term is the y-axis, and that is the y-intercept right there. See it? So the 0th term and the y-intercept are the same thing. So then I can say, here's my equation of a line. That's my Algebra 1 language. But you know what? We had other Algebra 2 language too. We had function rule. And this was the math that governed the input and output of a function. And we write function rules. We say, well, the output, which is the same thing as y, which is also the same thing as a sub n now, is equal to 2 times the input minus 3. Oh my goodness. Yes, there it is. So now we're back to speaking about inputs and outputs and functions. So I've got 3 different ways of writing the same thing. And this is kind of part of what Algebra 2 is all about. It's being able to see these things from different perspectives and understand that while I'm looking at them from different perspectives, they are in fact the same thing. It would be like as if I was staring at a statue in a museum that was in the middle of the room. I'm looking at it from the front, and then I can turn and look at it from the side, and I can turn and I can look at it from the back. All 3 of these are the same mathematical relationship, the same statue, but they each have a different perspective depending on, am I working with arithmetic sequences? Am I working with lines and graphs? Or am I working with functions and inputs and outputs? Okay? Now, when you do your homework, you're going to be asked to write an equation of a line. And if that's the case, then you need to use this language. Now, you're going to be asked to write the explicit formula for an arithmetic sequence. Then you're going to have to use this language right here. And if you're asked to write a function rule, you're going to have to use function language right here. And so you got to pay attention to what kind of language you're being asked to use so that you can then come up with the correct information. All right, that's it. So good luck. Go get them.